Hello students, welcome to the second year class of Computer Engineering and Information Technology for the data structure using C subject, and our subject code is 22317. So first we will see our today's video's learning outcome. As we are studying chapter number 5, trees and graphs. In this chapter we will going to learn about the graph adjacency representation. So first we will see what is graph representation. For the graphs to be computationally useful, they have to be conveniently represented in the programs. There are two computer representation of graphs. First is the adjacency matrix representation and adjacency list representation. So graph representation means space and time are analyzed in the terms of a number of vertices V and the number of edges E. There are at least two ways of representing graphs, the adjacency matrix representation and the adjacency list representation. So first, what is adjacency matrix? A square grid of a Boolean values if means the um, vertices and according to the vertices and edges. If the graph contains n vertices, then the grid contains n rows and n columns. For the two vertices numbered I and j, the element at row I and the column j is true if there is an edge from I to j, otherwise false. See here, this is the adjacency matrix and this is the graph. Okay. So this is the graph means 2 to 1, 2 to 4 and 0 to 0 to nothing means 3, 4 to 3 and 1 to 3. Okay. Now for the implementing adjacency matrix, see here, if the 0 we have to write in the rows and in the columns form, that is all the vertices. Means all these nodes. Means if there will be ABCD, then we have to write here ABCD. Now in this graph there is a 0, 1, 2, 3, 4. So we will write 0, 1, 2, 3, 4. So see here, this is the vertically and this is horizontally. And this is the columnar form and this is the row form. So first, if 0 means 0, we have to check the 0 to 0. Means firstly we have to check the self loop for 0 to 0. Okay, there is no loop for 0 to 0. So that's why it is false. And here we can write 0 also because no node there. So 0 to 1, that is no node means 0. It's all the 0 to 1, 0 to 2, 0 to 3, 0 to 4. There is no node from no edge from 0 to other number. That's why it is all these values are the false means 0. It's false, false. 0 to 2. Sorry, this has the value from 0 to 2. So that here we can write 1. So in this we can write 1. So 0 to 0 false, 0 to 1 false, 0 to 2 true, 0 to 3 false, and 0 to 4 false. Now 1. We will take node 1. Means 1 to 0, no node, no vertex, no edge. That's why false. 1 to 1 false. 1 to 2 false. 1 to 3 yes true, because 1 to 3 node is 1 to 3 edge is present here. That's why it is true. Then 1 to 4 false. So 2 to 0. 2 to 0 false. This is the directed graph. No? So it is 0 to 2, not 2 to 0. That's why this is false. So 2 to 1, yes, this is true. 2 to 3, false. Then 2 to 3 false, 2 to 4 true, because this is the node, this is the edge. Now next 3. So 3 to 0 false, 3 to 1 false, 3 to 2 false, 3 to 3 false, 3 to 4 false, because no outgoing edge here. Now 4. Now 4 to 0 false, 4 to 1 false, 4 to 2 false, 4 to 3. Yes, this is the no, this is the edge. That's why it is true. And 4 to 4 is false. Just like this, we can form a matrix by using these directions. That is called as the adjacency matrix. See here, this is the another example for this matrix. 1, 2, 3, 4, 5. Now this is the in these edges there are no direction. That's why this matrix will be different. So 1, 2. As usual, we have to write this is in the columnar form. All this node number and all the in the row wise all this node number. 1 to 5. This is 1 to 5. So first 1 to 1 0. 1 to 2 1. 1 to 3 1. 1 to 4 1. 1 to 5 0. Again 1 2. 2 to 1 1. 2 to 3 0. 2 to 4 1. 2 to 5 0. Now for the node number 3. 3 to 1 1. 3 to 2 0. 3 to 4 3 to 3 0. 3 to 4 1. Then 3 to 5 1. Now 5. 5 to 0. Now 5 to 1 0. 5 to 2 0. 5 to 3 1. 5 to 4 1. 5 to 5 0. Means if there will be a loop, then we can write this 5 to 5 is 1. Okay, this is the example of the adjacency matrix. So this is the directed multigraph. Now for this multigraph, the matrix is 1, 2, 3, 4. So it is 1, 2, 3, 4, and we have to consider as 1, 2, 3, 4. So 1 to 1, 1 to 1, 0. 1 to 2, yes, 3 nodes are there. 1, 2, 2, 1, 2, 2, 1, 2. So the value is 3. Then 1, 2, 3, 1, 2, 3, 0. Then 1, 2, 4, 1. Okay. Now this is 2. 2 to 1, 0. 2 to 2, this is loop. So 1. 2 to 3. 1, 2. So value is 2. Then 2 to 4, 0. Now 3. So 3 to 0, 3 to 1, 0. 3 to 2, this is 1 edge. That's why 3 to 2 is 1. And 3 to 3, these are the two loops in this for this vertices. For this vertex, there is a 2 loop. That's why value is 2. And the 3 to 4, 0. Now 4, 4 to 1, 0. 4 to 2, 0. 4 to 3, 0. 4 to 4, 0. This is the directed multigraph. Adjacency list representation. A graph of a n node is represented by a one-dimensional array L like linked list where L of I is the linked list containing all the nodes adjacent from node I. The nodes in the list L of I are in no particular order. So graphs, adjacency list. Adjacency list for each vertex V belongs to V store a list of vertices adjacent to the V. Example. Adjacent of a J of 1 is 2 of 3. Adjacent of a 1 is 2 and 3. Adjacent of a 2 is 3. Adjacent of a 3 is 0. Adjacent of 4 is 3. Means variation can also keep a list of edges coming into vertex. We have to consider only incoming edges. How much storage is required? The degree of a vertex V equal to hash indicates edges. Means directed graph has in degree and out degree. For a directed graph of a hash of atoms in adjacency list is the summation of out degree V equal to determinant of E. For the undirected graph, hash atom in adjacency list is summation of degree V equal to 2 into E. And so adjacency list take V plus E storage. See here the adjacency matrix. Again, now we will we are aware that how to form the adjacency matrix. Okay, A we have to write this is column, this is column wise, and this is row wise. Okay, A B C D E F. Now A B C D E F. Okay, A to A 0, A to B 1, A to C 0, A to D 1, A to E 0, A to F 0. Now B to A 1, then B to B 0, B to C 1, and like this. Means now C to A 0, C to B 1, C to C 0, then C to D 1, C to E 1, C to F 0, D. D to A1, D to B0, D to C1, D to E1, D to F0. Okay. Now F2 means F is a separate node. That's why all F2 A, B, C, D, E, F are zeros, all zeros. So if V comma W is equal to 1, if V comma W is in E, otherwise 0. Means we can say that if node is not a set of that graph, then we can directly write the 0 for this F node. Now adjacency matrix for a diagram. So this is the directional graph. This is the directional graph. So for the directional graph, if V comma W is in, then it is 1 and in, otherwise it is 0. See here, for this directional graph, A to B is 1, A to C, no, A to D is 1, okay, and means like this, B to A 0, B to B 0, B to C 1, okay, means this one. Now in this C, for the C node, there is only C to D and C to E. Okay, C to D and C to E. So for the D there is D to E, D to E. Okay. Then for the E, all are 0, and for the F, all are 0. So from this list, from this matrix, we can draw the list. So for each V in the V comma L, V equal to list of a W such that V comma W is in E. So firstly we have to write all the nodes. Then this is the linked list representation. This is the null list. Okay. So according to that matrix or this diagram, we can draw from A to B. So B and again B to B, again A to B and A to D. So A to B and A to D. So these are the two linked list. So A to B and B to D. Okay. Now next is a B. For the B, there is B to A and B to C. So B to A and B to C. Then C has the three linked list because C is connected to B, C is connected to D, and C is connected to E. C to B, then B to D, then E. And next D for the D. Again, there are three linked lists because D to A, D to C, D to E. Okay. Now for the E. E has the two linked lists, E to D and E to C. It's E to C and E to D. And finally F. F is a null. So this is the this is the linked list representation of the graph. This is the indirect. This is the linked, linked list representation for the directed graph. A is the source, E is the sink, and F is the disconnected from the rest. See here, this is A to B and A to D. This is A to B, D. Okay. Then B to C, then C to D and C to E. See here, then D, D to E. So D to E and E empty, F empty. Okay. Now this is the implementing graphs. So you see here, this is the value. Means this edges carry some values. This is that's why this is this includes the value. So a weighted undirected graph and its adjacency list. This is the weighted undirected graph. So as we know that we have to write the ABCD. Then from this list, so A to B, okay, and value is 8, and it points to the next node that is D, and A to D has the 6 value. That's why we have to write the values in this node. Now B to A, again the value is 8, and B to C, and the value is 9. Now then the B, and for the C, C to D, and value is 9. D to A, value is 6. Like this, we can implement the graph. Now, this is one example. Give the adjacency list of adjacency matrix for a given graph. So, this is the graph A, B, C, D, and E. So, we have to write, first we will draw the adjacency matrix. So, we have to write ABCD in the columnar form and ABCD in the row wise. Okay, now this is the directed graph. So A to A0, A to B1, A to C0, A to D0, A to E0. Okay. Now rest nodes are now B. So B to E is 1 and B to D is 1. Now B to A is 0, B to B is 0, B to C is 0. Now for the C, C to A is 1, C to B is 0, C to D is 0, C to E is 1. So 1 and 1. So D to A is 0, D to B is 1, D to C, D to E is 0, 0. Now E to A is 0, E to B is 0, E to C is 0, E to D is 1 and E to E is 0. So this is the adjacency matrix for this graph. Now adjacency list. So we see here this is the nodes A, B, C, D, E, and now we have to write the adjacency node, adjacent node. So A to B is the adjacent node. Then for the B, there is D and the D and E is the adjacent node. For the C, A and E is the adjacent node. For the D, B is the adjacent node. And for E, D is the adjacent node. Now the linked list presentation. See here, this is the linked list representation. So first A, B. From this list, we can draw this diagram easily. A, it has one linked list member is B. B has the two nodes, that is D and E. Then C has the two nodes, that is A and E. Now D has the one node, that is B, and the E has the one node, that is D. Okay, this is the linked list representation of this graph. With this topic, we have complete our chapter number 5, that is trees and graphs. Now we will see a difference between this tree and graph. So first difference is tree is a special form of a graph, that is minimally connected graph and having only one path between any two vertices. In the graph, there can be more than one path, that is graph can have unidirectional or bidirectional paths, means edges between the nodes. Now next is a tree. It's a special case of a graph having no loops and no circuits and no self loops. Graph can have loops, circuits as well as can have self loops. Tree traversal is a kind of a special case of a traversal of a graph. Tree is a traverse in pre-order, in order and post-order. Graph is a traverse by the DFS, means depth first search, and the BFS, breadth first search algorithm. So different types of a tree are binary search tree, avian tree, quick. There are mainly two types of a graph, directed graph and undirected graph. Tree application are sorting and searching like tree traversal or binary search. Graph application are coloring of maps in OR or PRT or CPM algorithms, graph coloring, job scheduling, etc. Trees always have a n minus 1 edge. In the graph, number of edges depends on the graph. Tree is a hierarchical model. Graph is a network model. This is the difference between the trees and the graph. Okay. Now we will see some MCQs. The number of element in the adjacency matrix of a graph having 7 vertices is 49. Okay. So next is what would be the number of zeros in the adjacency matrix of a given graph. So options are 10, 6, 16 or zeros, and the answer is 6. Now third question is for the adjacency matrix of a directed graph. The row sum is the dash degree and the column sum is the dash degree. Option is in out, out in total, total out. And the correct answer is out and in. Is for the adjacency matrix of a directed graph, the row sum is the out degree and the column sum is the in degree. So with this topic and as well as with this topic, we have completed our chapter number 5 as well as the overall syllabus of our data structure subject. Okay, now this is our last topic for this subject. So study well. Okay. Thank you.